This is section 1.7. 1.7 is about special systems of equations. It's called special because we didn't really know of a better word to tie things together than special. What you're going to see in this section are some things that are going to help us narrow down how many solutions we're going to have to a particular system. Okay, so let's take a look at 1.7. Special systems of equations. All right, given a system of linear equations, one of three things must happen. Now remember, we've been through this before. You either have to have infinitely many solutions, or no solution, or a unique solution. For linear equations, there's no way that we can get something different from one of these three. Like, there's no way that we could get just 2 solutions, or 7 solutions, or 5 solutions, or something like that. We'll either get infinite, none, or 1. What would happen, though, if we had a system that had more unknowns than equations? Meaning more variables than equations. For example, if you take a look at this system, or this augmented matrix which represents a system, here we have 3 variables. You know we have 3 variables because we have 4 columns, and the last one's the constant terms. So we had 3 variables in this system, only 2 equations though. Okay, 3 unknowns, 2 equations. Let's see what happens if we try to find the solution or solutions to this. Okay, if we reduce this using Gauss-Jordan elimination, we want to, it's already in reduced echelon form, so we want to convert it back to equation form. So we have x1 plus 2x3 is equal to -4, x2 minus 2x3 is equal to 1. And that gives us, solving for the one on the left, x1 is -4 minus 2x3, x2 is 1 plus 2x3. And remember, we had 3 variables, so I need to have something for x3, and so x3 is independent. Remember, anytime we have an independent variable, there are going to be infinitely many solutions. Okay, so this is a system that had infinitely many solutions. I started with 3 variables, 2 equations, and I got infinitely many solutions in this case. Let's look at another example. Here again, I have 2 equations because there are only 2 rows. But again, because I have 4 columns, I have 3 variables. So again, 3 variables, 2 equations. This time, when I go to convert it back into equation form, this bottom row gives me 0 is equal to 1. And remember, anytime you get something crazy like 0 is equal to 1, you have no solution. Okay, so see what a nice wrap-up this is to Chapter 1? You're getting a lot of the same old stuff you've seen, but kind of in a new package. All right, so that has no solution. So I had an example where I had 3 unknowns and 2 equations, and I got infinitely many. I had one where I got no solution. Is there a way that we could get a unique solution? Let's think about that for a second. To get a unique solution, we need to have a variable, or each variable equal to a specific number. So like, you know, x1 might be 1, x2 might be 2, and x3 might be 3. That would be a specific unique solution. Okay, so that's what I need to have happen in order to get a unique solution. I need to have a line for each variable. If I only had 2 lines, if I only had 2 rows, could I get a unique solution? Well, think about it. If I have 3 variables, I'm going to need at least 3 rows, right? So there's no way that I could get a unique solution if I only had 2 rows, because somebody would be left out. Okay? Geometrically, now that was if we looked at just the equations themselves, but geometrically, if we consider 2 planes, because remember, if we're dealing with a system of 2 equations, that would be 2 planes if we're talking about 3 unknowns. The only things that could happen is they could be either parallel, which means you wouldn't have any solution, or they could coincide, which means you'd get infinitely many solutions, or another possibility would be that they intersect in a line, but still we get infinitely many solutions. Okay, so you see there's no way with just two planes that you can get a unique solution. Okay, so that verifies what we just saw with the equations. And we even get a little theorem that says that too. If a system of linear equations has fewer equations than unknowns, so more variables than equations, it cannot have a unique solution. There's no way that it could have a unique solution. In other words, because there are only three things that could happen and we eliminated one of them, it's got to be one of the other two. It either has to have no solution or infinitely many solutions. Okay, so anytime you have more variables than equations, you'll either have no solution, it'll be inconsistent in other words, or you'll have infinitely many solutions. Okay, let's take a look at an example. Suppose a system has 3 equations and 4 unknowns. Okay, now 4 unknowns, 3 equations means more unknowns than equations. Okay, that was what the theorem was talking about, right? How many solutions is this going to have? Okay, remember the theorem said we can't have a unique. So that means it's either going to have no solution or infinitely many. We can't really say anything more than that, because that's all the theorem told us. We'd have to look at the particular system to determine any more than that. Okay, another example. This time it tells us a system has 3 equations and 4 unknowns, and it gives us the solution. x1 is 2, x2 is -1, x3 is 0, and x4 is 5. That's a solution. Notice it does not say is the unique solution. A lot of people will try to read in the word unique somewhere into that. It doesn't say that anywhere, okay? It just says it's a solution. This is something that does work for this system. Okay, now the theorem told us that if we have 4 unknowns and 3 equations, we have no solution or infinitely many. Now the fact that I have a solution means I can't have no solution. That would be stupid. So I have infinitely many solutions. You see how that works? Okay, so you just want to eliminate your possibilities. It's kind of like when you take a multiple choice test. If you can rule out a couple of those, then you've got your answer right there. All right, next, another example. Suppose the system has 3 equations and 3 unknowns. 3 equations and 3 unknowns. Does that theorem apply? The theorem specifically said you have to have more unknowns than equations, right? So that theorem doesn't apply to this situation since I have an equal number of equations and unknowns. It also tells us that x1 is 1, x2 is 3, and x3 is -2 is a solution. It does not say is the unique solution. It just says it's a solution. How many solutions does this system have? Well, that might be the only solution. I don't have anything that tells me it's not the only solution, right? But there could also be infinitely many. So there could be more solutions than that. I'm not given enough information to determine whether it's the only one or if there are more. Okay, next. We needed a definition, so I want to remind you of what a linear equation is. A linear equation is of the form a1x1 plus a2x2 plus a3x3 plus etc. plus anxn is equal to b. And that was where the a sub i's are the constants, called coefficients specifically. The x sub i's are variables, and b is a constant. Now I have the b bold-faced right there because the definition you're about to get uses that b. The definition says if the b is a 0, then the linear equation is called homogeneous. Okay, so you're getting the definition of what a homogeneous equation is. A homogeneous equation is one in which the constant term is 0. So if you were to put these equations into standard form is where you had all the variables on the left and the constant term on the right, all down that right-hand side you'll have zeros. That's how you can tell very quickly if a system is homogeneous. Just look at the right, bunch of zeros on the right, homogeneous. A homogeneous system is a set of homogeneous equations. All right, for example, you see here we have x1 plus 2x2 plus 3x3 is equal to 0, x1 plus x2 is equal to 0, and x2 plus x3 is equal to 0. That is a homogeneous system. It's all in standard form. I don't have any constants like over on the left that I need to move over to the right. It's in standard form, and everything on the right is a 0. So homogeneous. If I needed to find the solution to this system, and we're still going to have to do the reduction, but I wanted you to see that you can very quickly pick out a solution, because since everything's supposed to add up to 0, what if all the variables themselves were zeros? Okay, for example, if I plug in a 0 for x1, and then 2 times a 0 for x2, and then 3 times a 0 for x3, I do get 0. You can check again. 0 plus 0 is 0, and 0 plus 0 is 0. So 0, 0, 0 is a solution. Now, I don't know for sure that that's the only solution, but I know it is a solution, just very quickly from checking. And that'll always apply with a homogeneous system. Since everything's supposed to add up to 0, then 0, 0, 0 will always work. Okay, we'll have to reduce to see if that's the only solution, though. Okay, so toss that thing into an augmented matrix and start the reduction process. I have a 1 in the upper left-hand corner. That's a good sign. I need a 0 where this 1 is. All right, so I have a 1 in the second row. I need to be a 0. I already have the 0 that's in the third row. So as far as the first column is concerned, all I need to do is row 2 minus row 1, and that'll fix that 1 that's in the second row. Okay, now my first column looks like 1, 0, 0. That's what I want. Next, move to your second column. You want a 1 where that negative 1 is. Now, you're perfectly welcome to multiply by negative 1. That'll make that a positive 1. I happen to choose to switch row 2 and row 3. But it's your choice. We may take different steps, but remember there was a theorem way back that said we'll all get the same answer in the end. Okay, once I switched row 2 and row 3, I've got the 1 in the correct position now in the second column. But I want the 2 above it to be a 0. I want the negative 1 below it to be a 0. So I need to do row 1 minus 2 row 2 and row 3 plus row 2. That's going to make each of those a 0. So across the top row now I have 1, 0, 1, 0. And then the bottom row, 0, 0, negative 2, 0. Okay, now I need for that negative 2 to be a 1. And you can accomplish that best without messing up some other stuff by doing negative 1/2 of row 3. Just multiply by its reciprocal, and its reciprocal is negative 1/2. Okay, that gives us a 1 in that position. Then I need to clear up the rest of that column. I need for these two 1s to be 0s. So if you do row 1 minus row 3 and row 2 minus row 3, now it's in reduced echelon form. Okay, now what I get from that then is that x1 is 0, x2 is 0, and x3 is 0. That means that was the unique solution. That was the only solution that I got to that particular system. Okay, so in general, I can look at a homogeneous system and I can say, well, it's either going to have a unique solution 0, 0, 0, or if it's two-dimensional, obviously 0, 0. Or it could have infinitely many. Now, if it's infinitely many, then you're going to get an independent variable. In this particular one, I did not get an independent variable. Okay, any homogeneous system will have x1 equal to x2 equal to xn equal to 0 as a solution. Again, it may not be the only solution, but it will be a solution. That's called the trivial solution. The trivial solution is when all the variables are equal to 0. And that trivial solution is going to work for any homogeneous system. There's even a theorem, and the theorem says, given a homogeneous system of linear equations, exactly one of the following possibilities holds. Either A, the system has exactly one solution, which would be that trivial solution, that was like the example we just saw, or the system is going to have infinitely many solutions. And if it has infinitely many solutions, it's going to have solutions that aren't the trivial solution, obviously, so we just call those non-trivial solutions. Now, non-trivial just means that it's something other than all zeros. It could be like 1, 1, 0, 0. You know, it could have some zeros in it, but it's just saying that all the variables aren't 0. There's one, at least, that's not a 0. All right, in other words, again, a homogeneous system will always be consistent. I can't have an inconsistent homogeneous system because you know that you're always going to have that trivial solution. That's always going to work for any homogeneous system. All right, another theorem. Putting those two ideas together, we said a homogeneous system can't be inconsistent, right? And we also said something earlier about a linear system. If it has more unknowns than equations, that I couldn't have a unique solution. So what if I had a homogeneous system with fewer equations than unknowns? Putting the previous two theorems together, I have this new theorem that says that system has to have infinitely many solutions. So if a homogeneous system has infinitely many solutions, it's going to have non-trivial solutions. It'll have the trivial, obviously, but it will also have non-trivial. Okay, so what could I say about this system? I have a homogeneous system. It has 3 equations and 4 unknowns. What's that tell me? Okay, homogeneous meant that of my 3 possibilities, my none, 1, or infinite. Okay, remember that always has to happen. I can't have the none situation. A homogeneous system will either have 1 or infinite. Now the fact then that it tells me I have more variables than equations rules out the 1. So what about this system? It's going to have infinitely many solutions. Okay, so again, it will have non-trivial solutions. It will have the trivial as well as non-trivial solutions. Infinitely many solutions. Next, what can you say about a homogeneous system of 3 equations and 3 unknowns? Okay, 3 equations and 3 unknowns. Does that very first theorem that we did, something about more unknowns than equations, does that apply here? No, it doesn't. Okay, so the only helpful information that I have here is the fact that it's homogeneous. Because it's homogeneous means it's not going to be inconsistent. So I'm either going to have only the trivial solution, which would be the unique solution, or it could have infinitely many solutions. So it would have non-trivial in that case. So I'm not able to say anything more than, well, it's not inconsistent. Okay, it's got to be consistent. It's got to have at least one solution, but it might have infinitely many. And that's as much as I can say about that system. All right, what about this one? This time I have a homogeneous system, 3 equations, 3 unknowns, and it gives us x1 is -1, x2 is 0, and x3 is 4 as a solution. Notice it does not say as the unique solution. That would be an inconsistency anyway, because there's no way that a homogeneous system would have something other than 0, 0, 0 as its unique solution. Okay, so what it's saying is that I have a solution of -1, 0, 4, and it's homogeneous. Now, because it's homogeneous, I also have 0, 0, 0. That tells me about 2 of the solutions. I have 0, 0, 0, I have -1, 0, 4. Was that something that can happen with a linear system? Can I have exactly 2 solutions? No. We said originally you either have none, 1, or infinite. Okay, I know about 2. So that means what? There have to be infinite. There have to be infinitely many solutions. Okay? I'm hoping this is making sense. That was a non-trivial solution that it gave us to a homogeneous system. So there have to be infinitely many solutions. All right, next. Note that the above theorems apply to systems that have more unknowns than equations, more variables than equations. There are not any theorems for systems with more equations than unknowns. Okay, so if I have a whole bunch of rows and just a few variables, it's not going to help me determine how many solutions there are. All I'm really concerned with is, are there more unknowns than equations? Are there more variables than equations? Not the other way around. Okay. Let's look at another example. This is the last one in this section. If the points P, which is -1, 0, Q, which is 2, -3, and R, which is -3, 12, are on the graph of the parabola y equal to ax squared plus bx plus c, I want us to be able to find A, B, and C. Okay, I'm given 3 points that are on a parabola. I'm given the equation of the parabola, except that I want to be able to find the A, B, and C. Okay, where a lot of people get confused on this one, and maybe you're confused too watching this, is that you're used to the x and y being the variables. But in this particular example, the x and y are not variables. They are the points that you're given. The variables that I'm looking for, well, I mean, they're variables in general. X and y are variables in general. But the variables that I'm looking for, the ones I'm solving for, are A, B, and C. And once you make that distinction, it's a whole lot easier to solve this thing. Okay, specifically what's going to happen is if you take the point P, that is an x value and a y value. The x value is -1, the y value is 0. So if I plug in that x value and y value, I get an equation. I get 0 is equal to a times -1 squared plus b times -1 plus c. If I take the Q point, x is 2, y is -3. I get -3 is equal to a times 2 squared plus b times 2 plus c. Then if I take the R point, there x would be -3, y would be 12. I get 12 is equal to a times -3 squared plus b times -3 plus c. Now you can probably see, once you've plugged in for x and y, you can see how I have 3 equations. I have 3 unknowns. My unknowns are a, b, and c. Do any of the theorems that I went over earlier, do any of those apply in this situation? No, they don't, because I don't have a homogeneous system. I have one homogeneous equation, but the whole system itself is not homogeneous, so that didn't help me. And I have an equal number of equations and unknowns, so none of the other theorems apply either. Okay, so this is kind of a good example for you to see when theorems don't apply. All right, so in order to solve this, what I'm going to need to do is first put these things into standard form. Okay, so I just rearranged it to where the variables were on the left, the constants were on the right. And then I just want to drop that into an augmented matrix and then solve it. Okay, I'll spare you the pain and agony of going through all the steps solving it. What you want to do, of course, is to start by getting the 4 that's in the second row to be a 0, and the 9 that's in the third row to be a 0, and so on. And once you finish, this is going to reduce down to 1, 0, 0, 1, 0, 1, 0, -2, 0, 0, 1, -3. And what that means for me is that A is equal to 1, B is equal to -2, and C is equal to -3. I know you're used to that being x1, x2, and x3, but in this case, the first column was representing the coefficients of A. The second column was representing the coefficients of B, and the third column was representing the coefficients of C. So when I finish up, I have A, B, and C. Now I know the equation to that parabola, because I was told it was ax squared plus bx plus c. So I can tell you now the equation to the parabola is x squared minus 2x minus 3. had a unique solution. Okay, so that was section 1.7. As you saw, it's a pretty good wrap-up to chapter 1. Chapter 1, you saw Gauss-Jordan elimination for the first time. You saw augmented matrices for the first time. You saw consistent and inconsistent systems of equations that had a unique solution or infinitely many solutions. And then in 1.7, you're going to get all of those all over again, plus the nice little theorems that help us narrow down which of those it's going to be. Okay, so practice with this one a little bit. Like I said, it'll wrap up probably some of the loose ends in the previous sections, and so if you have trouble in 1.5, for example, 1.7 might make that a little more clear. But do spend some time with this one, and it should go really well.